I want to take a look at another integral that doesn't immediately scream out and say, hey, here's a trig sub, but it does end up needing a trig substitution with a little bit of algebraic manipulation ahead of time. The thing is with the trig substitutions, we're always looking for a sum of two squares, a squared plus b squared, or a difference of two squares, a squared minus b squared, one way or the other. And this has got a squared in it, but it's got this linear term in it as well. But what I'm going to do is to turn it into what I want is I'm going to do a complete the square underneath the square root there. So I'm going to look at this like this. If there was anything other than the 1 in front of the x squared, I'd factor it out of these two, but it is a 1 right there. So I'm looking at the t, sorry, not x, but t squared minus 6t. I'm going to put the plus 13 over here just for safekeeping. And I want to look at that and complete the square. Now, you might remember how to do this. I might have to remind you. Anyway, to complete the square, you take this number, you cut it in half. That would be 3. And then, well, negative 3, and then you square that to be 9. So really what I want here is I want a plus 9. Well, I can't just go adding 9 everywhere I want. I have to compensate by, actually, let's just do it right here, subtracting 9. So I'm adding 0. But I did it in a way that it made part of that look like a perfect square. That is, now this looks like this bit right here, from there to there, is t minus 3 squared. And then the minus 9 plus 13 is 4. Let's do that without the question mark. 4. There we go. dt. So now what I have is not quite the same as what I had before, but still similar. With a plus sign in between here. This is a perfect square plus another square. So I'm looking at something that looks like maybe my 1 plus tangent squared theta equals secant squared theta. But it's not a 1, it's a 4, so let's multiply by 4. So 4 plus 4 tangent squared theta equals secant squared theta. Okay, so that's what I'm going for. What I have is 4 plus t minus 3 squared equals, what I want it to equal is 4 plus 4 tangent squared theta. So essentially now I'm going to solve for t. T minus 3 squared is 4 tangent squared theta. Take the square root. T minus 3 has to be 2 tan theta. And t is equal to 3 plus 2 tan theta. Right? A little more complicated than I had before, but still, this is what I want to do. I want to let t equal 3 plus 2 tan theta. And one of the things I see is if I take that and I plug it in, what happens to t? The first thing is you subtract 3, so this will go away. Then I've got 2 tan theta. Well, that gets squared, so the 2 becomes a 4, and the tangent becomes a tangent squared, and I end up with just what I wanted. 4 tangent squared theta plus, there's the plus 4. Okay. So with t equal to 3 plus 2 tan theta, dt would be the derivative now, which is 2 secant squared theta d theta. And I plug in. So I've got the integral, there's a 1 on the top. Well, the t minus 3 squared, as we just said, the 3 first of all gets subtracted off, and then you end up with a 4 tangent squared theta plus 4 under the square root there. The dt is, I'm just going to write it in the numerator, is 2 secant squared theta d theta. Okay. So what do I end up with here? I've got an integral of 2 secant squared theta d theta, and the denominator, well, let's see if I've got it right here. That 4 plus 4 tangent squared theta that I see under the square root is secant squared theta. And so when you take the square root, you're just left with the secant of theta. So I end up with the integral of 2 times the secant of theta d theta, which I happen to know is the natural log of the absolute value of the secant of theta plus the tangent of theta plus c. Now I need to get back into x's, or t's in this case, and this was my substitution right here. So there's a triangle involved here. If I solve for tangent of theta, it's t minus 3 over 2. So if I draw this triangle, call that theta, tangent is the opposite side over the adjacent side. So if I say t minus 3 here and a 2 right there, then the length of this other side is equal to this squared plus that squared. So t minus 3 squared plus 4 squared, and then, sorry, 2 squared, which is 4, and then the square root of all of that, which is the thing that we had back up here, right? That this hypotenuse that we just calculated is the same as the square root that we had right there. Good. That's always a good sign. So now I can substitute back in, because I know that the secant of theta is this divided by that. So hypotenuse divided by adjacent, square root of t minus 3 squared plus 4 divided by 2, plus the tangent of theta, which is this divided by that, t minus 3, that's opposite over adjacent, over 2 plus c. Now, one of the things that you're going to find is if this were a problem in the homework, which actually I think it is, yeah, this is number 24. Well, maybe you weren't assigned this one. But if you look in the back of the book, they don't have the 2's. Their answer is this whole thing without the 2's. They get rid of that 2 and get rid of that 2. It's like, well, yeah, you can't just do that. Well, you can do anything you want as long as you do it right. And notice what happens here is inside here, there's a sum of two fractions. They have a common denominator. So this is 2 times the natural log of the absolute value of just one fraction here, which would be the square root of t minus 3 squared plus 4 plus t minus 3 all over 2. And then they notice that, oh, this is the log of a quotient. So they can rewrite this as 2 times the natural log of the numerator, sorry, absolute value of the numerator, t minus 3 squared plus 4, that's a 4 up there, plus t minus 3, minus the natural log of the denominator, which is 2, plus a constant. And that should be an absolute value sign. And then they notice if you distribute the 2 through, this is 2 times the natural log of this thing, square root of t minus 3 squared plus 4 plus t minus 3 minus 2 natural log 2 plus a constant. The thing is, 2 natural log 2 is just a constant. So they look at this whole thing and they say, oh, let's just call that plus c. So that 2 disappears because it ends up being absorbed into the constant. One thing to keep in mind, as you're looking up your answers in the back of the book, quite often there'll be these subtle little differences. You say, what, I've got a 2 in there and they don't have a 2 in there. Well, see if you can manipulate it to get the 2 to disappear, or essentially be swallowed up by the deep blue sea here. Anyway, so 2 things that we looked at there. One is that answer potentially being different than the back of the book. And the other thing is, what do you do when what you're starting with isn't just a sum or a difference of squares? If it's a quadratic polynomial at all there, any quadratic polynomial, you can do a complete the square on it to turn it into either a sum or difference of squares. This might have turned out, if I had to add and subtract 15, then this would have been a minus 15 plus 13, so this might end up being a minus 2, right? That, depending on what you have to add and subtract, determines whether the sign here is plus or negative. Okay. So anyway, there you go. There's another technique that works with trig substitutions.